In this video, I'll talk about Eratosthenes' measurement of Earth's diameter. How did he measure the Earth's diameter 2000 years ago, or almost 276 years before Christ? Eratosthenes was a great mathematician, and he calculated the Earth's diameter 2000 years ago with remarkably high accuracy. And how did he do it? And he did it by simply using a pole and a hole. So what does that mean? So now let's assume you have two poles here, and he in fact inserted two poles into the ground, one in Syene and one in Alexandria. These two poles are about 500 miles apart, and he measured the shadow's length. What he observed, that the length of the shadow is almost zero. That means the sun is on the top, directly overhead. So the length of the shadow in Syene was zero, and he did it on the longest day of the summer, which is June 21st. And on the same day, what he observed, that the sun is not directly overhead, it is making some angle here. And then from just this observation, he convinced himself that the earth is not flat, it is spherical. And how he came to the conclusion that earth is not flat but rather a curved surface? Let's talk about that one. We know that the sun, and in fact he knew that the sun is very, very far from the earth's surface, and also it is gigantic in comparison to the earth. So if the sun is far, far away, all the light rays that is coming to the earth's surface must be parallel. So these light rays represents the parallel light rays coming from the sun surface. Okay, and if the light rays are parallel, and if you assume, let's say if we assume the earth is flat, if earth is flat and the light rays are coming parallel, then the length of the shadow would be exactly the same. But that was not the case. He observed in Syene that the length of the shadow was close to zero. There was no shadow at all, in fact. And in Alexandria, he observed there was some shadow. So this made him believe that the earth is not flat but rather spherical. Now let's talk about the spherical assumption of earth's surface. So now let's say if earth is curved, not flat, then the light rays coming here, this is the pole in the Syene and this is the pole in Alexandria. If you are here, if you insert a pole, it has to be perpendicular to the surface here. And if the light rays are coming parallel from the sun's surface, then if the sun is directly overhead in Syene, then it makes sense the length of the shadow would be zero. But at this point in Alexandria, these light rays are not coming directly overhead but rather at an angle. So you would observe this angle here. Now this observation completely resonated with the other observation that earth is not flat but curved. So from these two observations, you see, if it is a flat, then you would observe the same length of the shadow everywhere. But if the earth is spherical, the length of the shadow, if you measure on the same day, here all the observations are on the same day, not on a different day. Just keep in mind, these observations are on the same day. So Earth, now he was totally convinced that Earth is not flat but rather a spherical or curved surface. Now we'll talk about how did he used a simple trigonometry, simple math to calculate the Earth's radius or the diameter. Let's talk about that one. So here, this is the A stands for Alexandria here, which is a small city, and this is in Syene, which is another city, and there's a well here, or a hole, a big hole there. And on June 21st, when the sun was directly overhead, the light just passes through it. Okay, that means there is no shadow at all. And on the same day in Alexandria, he inserted a pole into the ground. And what he measured, there is an angle between the pole and the light rays. Or in other words, there is a shadow here. And if you connect these two lines, then this is the angle between the pole and the light rays. Now, if we project these two, the pole and the light rays, all the way, it will intersect at the center of the Earth, because these two are perpendicular to the surface here. So if we project it all the way, it will intersect at the center of the Earth. Now, just by measuring, he measured the length of the shadow, and he also measured the length of the pole. From these two observations, he calculated this angle theta. How? So if you know, let's see here, in the tangent theta, here would be the length of the shadow divided by the length of the pole. So we know this, he knew the length of the shadow, he measured it, and he also measured the length of the pole. And from this observation, he calculated this angle theta. And at the time, this angle was 7.2 degree. 7.2 degree. Now remember, this angle is exactly equal to this angle. How? Because these two are the parallel light rays. So these two angles will be alternate angles. So this angle is exactly equal to this angle. Okay. So, and remember, the distance between Alexandria and the Syene was 500 miles. Okay, 500 miles. Now let's focus onto this sector here, this tiny sector here. Compared to the Earth, this is a tiny sector. So in this tiny sector, we know this arc length and we know this angle here. So now we know the relation is theta equals to L over R, or he at the time used the same equation here. Theta is L equals L over R, and in this case, if you use L over R, that means the theta is in radian, and he had measured in degree, so we have to change the radian into degree, and you know that the pi radian is equal to 180 degree. So here I'm just changing the radian into degree, so you simply have to multiply it by 180 over pi. So in that case, theta will be in degree now. Now from this equation, we just can simplify or solve for R. R will be L times 180 divided by theta pi. The L is the arc length, this length here. And theta is the angle, this angle here. Now let's plug in all the values. So once we plug the value, theta is 500 mile, the arc length, this is the arc length here, and theta is 7.2 degree, and solve it, what you get is the R The radius of the Earth is 3981 mile, 3980 mile, and the modern measurement of the Earth radius is 3959 mile. This is the average radius of the Earth. So if we calculate the percentage uncertainty in the measurement, or what is the percentage error compared to this value and this value, it is 0.6%. 2000 years ago, just by using a pole and a hole, he calculated the Earth's diameter or the radius, and the percentage difference is only 0.6%. This is remarkably well done, and nothing can be done better than this. So this is an absolutely wonderful observation and the measurement, and this is how he calculated the Earth's diameter. So again, if you have any questions regarding his method of measurement, please write your questions in the comment section below, and do not forget to subscribe my channel. Thank you so much.